On March 7, 2025, the Aramark STAR Complex at Temple University buzzed with excitement as students from grades 6 through 12 showcased their innovative projects at the annual George Washington Carver Science Fair. This event, which has become a staple of the Philadelphia educational landscape since its inception in 1979, was designed to inspire young minds and provide a platform for budding scientists to explore their interests in STEM science, technology, engineering, and mathematics. Sponsored by Temple's College of Science and Technology and the Office of Community Affairs and Engagement, the fair drew participants from public, charter, parochial, and private schools across the region. Among the standout projects was Veronica Gonzalez's intriguing exploration titled Non-Dominant Arm versus Robotic Arm. With a homemade prosthetic arm crafted from everyday materials like cardboard and syringes, Gonzalez captured the attention of attendees as she demonstrated the arm's capabilities. The syringes I use can hold up to 10 milliliters of water to pump water into the prosthetic arm model, allowing it to effectively move in multiple directions and grab objects, explained Gonzalez, a student at Philadelphia Academy Charter High School. Her findings revealed that while her robotic arm could lift larger items, it struggled with smaller ones, highlighting the challenges faced in prosthetic design. Inspired by her experiences visiting hospitals where children use prosthetics, Gonzalez hopes to pursue a career in creating advanced prosthetic devices. Another promising project came from Ja'kiyah Wright, who presented her research on the impact of trees on local weather patterns. Titled Canopy Climate Control, Wright's project compared temperature readings from two parks in Philadelphia, revealing a surprising 10-degree difference between the more wooded Markward Park and the less vegetated Diamond Park. I expected there to be a difference of 4 to 5 degrees, so I was surprised to discover there was a difference of 10 degrees, Wright remarked. Her work not only showcases the environmental significance of urban forestry but also reflects her commitment to enhancing community green spaces. The George Washington Carver Science Fair serves as a critical stepping stone for young students, immersing them in an academic atmosphere that encourages curiosity and innovation. Our mission is diversity in STEM education with a commitment to community, stated Neferteri Gist, a TUteach mentor and instructor at the College of Science and Technology. Gist emphasized the importance of creating an inclusive environment where students from all backgrounds can engage with science and explore their potential. As the fair concluded, it was evident that events like these are essential for nurturing the next generation of scientists and innovators. By providing a platform for students to express their ideas and findings, Temple University continues to foster a culture of inquiry and enthusiasm for scientific exploration. Looking ahead, it is crucial for educational institutions to maintain this momentum, ensuring that young minds are equipped with the skills and confidence needed to tackle the complex scientific challenges of the future. In recent developments surrounding mRNA vaccines, significant changes within the research landscape have raised concerns about the future of vaccine development and public health strategies. The National Institutes of Health (NIH) has made headlines by terminating at least 33 grants aimed at studying vaccine hesitancy, with a particular focus on mRNA vaccines during a critical period marked by a resurgence of measles outbreaks across the U.S. This decision, framed as aligning NIH priorities with current health policies, could have profound implications for understanding and addressing vaccine skepticism. Acting NIH Director Michael Memoli's directive to streamline research grants has drawn attention for its timing and implications. The cuts come as the nation grapples with one of the largest measles outbreaks in recent history, predominantly affecting unvaccinated populations. With 253 reported cases, including 2 fatalities, the urgency of vaccine uptake has never been more critical. It is the policy of NIH not to prioritize research activities that focus on gaining scientific knowledge on why individuals are hesitant to be vaccinated, the termination letter stated, reflecting a shift away from exploring the complexities of vaccine acceptance. This abrupt pivot in NIH funding is further complicated by the appointment of Robert F. Kennedy Jr. as the new Secretary of Health and Human Services. Known for his controversial stance against vaccines, Kennedy's influence on health policy could steer the NICE's research agenda toward a more skeptical view of vaccination, which many fear could erode public trust in science and medical recommendations. Simultaneously, Moderna, a key player in mRNA vaccine development, faces its own set of challenges as its stock has plummeted by over 51% since September 2024, raising questions about the company's viability and future in this competitive market. Analysts have cited tumbling revenues and negative cash flow margins as major red flags. These financial struggles are compounded by concerns that Moderna may soon need to raise capital from investors, potentially diluting shareholder value. Unless Moderna's fundamentals change quickly, it might find itself in a position where it must raise capital from investors to continue operating, warned an analyst. Highlighting the precarious balance the company must maintain. The ongoing discourse surrounding mRNA vaccines is becoming increasingly polarized. While some emphasize the potential of mRNA technology to revolutionize treatment for various diseases, including those deemed undruggable, others point to the risks associated with these therapies. The challenges of delivering mRNA therapeutics effectively, coupled with concerns over stability and immune responses, remain significant hurdles that researchers must overcome. As public health officials and researchers navigate this complex landscape, the implications of these developments are far-reaching. The NIH's decision to cut funding for vaccine hesitancy research could stifle efforts to understand and mitigate the factors contributing to vaccine reluctance. In parallel, the financial instability of companies like Moderna may hinder future advancements in mRNA technology, raising concerns about the sustainability of innovations that have the potential to reshape medicine. Looking ahead, it is crucial for stakeholders in public health and biotechnology to advocate for comprehensive research that addresses vaccine hesitancy and to foster transparency in the development and funding of new medical technologies. As the situation evolves, the interplay between public policy, scientific research, and corporate health strategies will undoubtedly shape the future of vaccination efforts and public health outcomes in the United States and beyond. A recent study from Arizona State University has uncovered intriguing insights into the complex interplay between diet, blood sugar levels, and cancer risk across various vertebrate species. As researchers continue to probe the depths of cancer biology, this comprehensive analysis sheds light on evolutionary adaptations that could potentially inform human health strategies in cancer prevention and treatment. The study, published in the journal Nature Communications, involved an exhaustive examination of diet, average plasma sugar levels, and cancer prevalence across 273 vertebrate species. Researchers found that, contrary to conventional beliefs, there is no significant link between diet and plasma sugar levels among non-human vertebrates. This suggests that evolutionary and physiological adaptations may play a more vital role in glucose regulation than diet alone. Notably, birds were a standout in this study. Despite exhibiting higher blood sugar levels, they demonstrate a surprisingly lower prevalence of cancer compared to mammals and reptiles. Co-author Carlo Meli, a researcher at ASU's Biodesign Center for Biocomputing Security and Society, stated, "We knew that birds get less cancer than mammals, and they also have very high levels of glucose in their blood. That made us wonder if there was some connection." This connection is pivotal, as it could unveil unique biological defenses against cancer that evolved in certain species, potentially offering insights for human applications. The research revealed that primary carnivores, which predominantly consume other vertebrates, are more susceptible to tumors than herbivores, particularly when domestication is taken into account. This finding raises questions about dietary influences on cancer risk, suggesting that harmful compounds may accumulate along the food chain, thus increasing tumor development risk in carnivorous species. Stefania Kapsataki, the study's corresponding author, emphasized the need for further exploration into how evolutionary history intersects with dietary habits and cancer prevalence. Future studies investigating the evolutionary history and mechanisms linking diet, plasma glucose levels, and cancer prevalence across vertebrates would provide further clues about the observed diversity among species and inform strategies for more effective cancer prevention and treatment across vertebrates, she noted. Although the study concluded that diet does not uniformly influence blood sugar levels across species, it highlighted that domesticated animals tend to have a higher cancer prevalence, possibly due to reduced genetic diversity and weaker evolutionary pressures. This underscores the role of natural selection in limiting cancer in wild populations, while also emphasizing that the research does not imply increased cancer risk from consuming domesticated animals. The implications of these findings extend beyond non-human species, suggesting that understanding the unique adaptations that confer cancer resistance in birds could inform future cancer prevention strategies for humans. Unlike birds, humans and other mammals do not exhibit the same level of resistance to cancer despite high blood sugar levels. The researchers proposed that the unique biological mechanisms in birds, such as their high metabolic rates and adaptations that limit oxidative damage, could provide valuable insights into developing novel cancer prevention strategies. As researchers continue to unravel the complexities of cancer biology, the study paves the way for future investigations that might one day lead to breakthroughs in cancer treatment and prevention. For now, the best advice for humans remains consistent: maintain a balanced diet, limit processed and red meat consumption, and manage blood sugar levels through a healthy lifestyle, including regular exercise. The ongoing quest to understand nature's cancer-resistant species could ultimately enhance our approaches to combating this pervasive disease. In a groundbreaking initiative that merges artificial intelligence with healthcare, researchers at Texas A&M University are on the verge of revolutionizing dental surgeries. Dr. Yuxiao Zhou and Dr. Jae-Sun Lee have been awarded the prestigious 2024 SEED program for AI computing and data science from the Texas A&M Institute of Data Science for their innovative project titled "Toward Smart Orthopedic Surgery Planning by Using Physics-Informed Machine Learning." This recognition cements their position at the forefront of AI-driven advancements in medical technology. Dental implant surgeries play a crucial role in enhancing the quality of life for many, particularly the aging population. However, the success of these procedures hinges on achieving optimal mechanical stress levels in the surrounding bone during everyday activities like chewing. Insufficient or excessive loading can lead to complications such as bone loss or fracture, posing significant challenges especially in older patients who often experience delayed bone healing and varying bone stiffness. Current methods for assessing bone stiffness can be invasive and computationally demanding, underlining the critical need for more efficient, patient-specific solutions. Zhou and Lee's response to this challenge is a hybrid biomechanical model that integrates physics-informed machine learning with real-world bone deformation data. This cutting-edge approach allows for precise, personalized predictions of mechanical stress in the bone, significantly enhancing dental surgery planning. Our model will revolutionize surgical planning by delivering personalized, computationally efficient treatment plans with predictable outcomes, stated Zhou, highlighting the transformative potential of their work. What sets this project apart is its interdisciplinary nature, drawing on Zhou's expertise in mechanical engineering and Lee's background in machine learning for healthcare systems. Their collaborative effort not only aims to improve dental implant procedures but also holds promise for a wide range of surgical applications across the healthcare sector, potentially reshaping surgical practices in various specialties. The recognition from the SEED program underscores Texas A&M's commitment to fostering research that drives tangible real-world impacts. As this innovative project progresses, it may pave the way for AI's broader integration into medical practices, enhancing patient outcomes and redefining standards of care. Looking ahead, the implications of this work extend far beyond dental surgery. As the field of AI continues to evolve, the potential for similar advancements in other areas of healthcare remains vast. The success of Zhou and Lee's project may inspire further research and development in AI-driven medical technologies, ultimately improving the quality of healthcare for patients worldwide. The future of surgical procedures could very well be shaped by the integration of intelligent systems that personalize and optimize treatment in ways previously thought impossible. In a remarkable leap forward for fusion energy technology, researchers are exploring innovative solutions that could revolutionize the field. Recent advancements include the development of new computer code that simplifies the design of stellarators, an alternative to traditional tokamaks, and the creation of microbatteries powered by nuclear waste. These breakthroughs hold significant potential for the future of sustainable energy. At the forefront of these developments is the research conducted by scientists at Ohio State University who have devised a method to harness the latent energy in nuclear waste. Utilizing scintillator crystals which emit light when exposed to gamma radiation, the team has successfully paired these materials with solar cells to create microbatteries. These batteries, while not yet capable of powering homes, can generate hundreds of nanowatts, enough to operate microsensors. "We're harvesting something considered as waste and by nature trying to turn it into treasure," said Raymond Chow, a co-author of the study. As the world seeks to expand its reliance on nuclear energy, projected to increase by 2.5 times by 2050, this approach could transform nuclear waste from a liability into a valuable resource. Meanwhile, General Fusion, a Canadian company, has achieved a historic milestone by successfully igniting plasma within a steam-powered nuclear fusion reactor. This achievement, realized in their Lawson Machine 26 LM26, marks a significant stride in magnetized target fusion (MTF) technology, which aims to produce clean energy without the high costs associated with conventional methods such as superconducting magnets. Dr. Michel Laberge, the company's founder, expressed pride in the achievement, noting, "We've built 24 plasma injectors, created over 200,000 plasmas, and generated fusion neutrons from plasma compressions." The LM26 reactor, which can potentially provide power to 150,000 homes, operates by driving pistons that compress plasma, creating conditions conducive to fusion. In parallel, a new computer code has emerged that significantly reduces the design time for stellarators, which are complex devices that use magnetic fields to confine plasma. This breakthrough, developed by researchers at the Massachusetts Institute of Technology and Princeton University, aims to streamline the intricate process of designing these devices, which have long been seen as a viable path to achieving sustainable fusion energy. The new code is expected to enhance the efficiency of stellarator design, potentially accelerating their deployment in energy generation. These advancements highlight a broader trend in the fusion energy sector, where innovative approaches are being explored to overcome the challenges that have historically hindered the commercialization of fusion power. As the global energy landscape continues to evolve, the integration of new technologies such as waste-derived energy sources and advanced computational models may play a crucial role in shaping a sustainable energy future. With these promising developments, the countdown toward practical fusion energy appears to be more optimistic than ever. As researchers continue to refine their technologies and methodologies, the prospect of affordable clean energy could soon transition from a distant dream to a tangible reality. The coming years will be critical in determining how quickly these innovations can be scaled up and integrated into existing energy systems, potentially altering the very fabric of global energy production. The quest for room temperature superconductivity has taken a significant leap forward, rekindling hopes that have flickered for over a century. A recent study published in the Journal of Physics, Condensed Matter posits that the fundamental constants of the universe do not preclude the existence of a material that could exhibit superconductivity at room temperature, an idea that could revolutionize technology as we know it. Superconductors, which are materials that can conduct electricity without resistance, have long been limited to extremely low temperatures, creating a barrier to their widespread application. The notion of a room temperature superconductor has been sought after since Dutch physicist Heike Kamerlingh-Onnes first discovered this phenomenon in mercury in 1911. Since then, advancements have been sporadic. The 1980s saw the emergence of high-temperature superconductors, yet these materials still require cooling far below what is considered comfortable. Recent controversies, including the retraction of a 2023 paper on a claimed room temperature superconductor, have only added to the skepticism surrounding this elusive goal. The new research, spearheaded by physicists from the University of Cambridge and Queen Mary University of London, offers a refreshing perspective. By analyzing the fundamental constants such as the Planck constant, electron charge, and electron mass, The researchers have calculated that the maximum critical temperature Tc for superconductivity could range between 100 to 1000 Kelvin, approximately -280 to 1340 degrees Fahrenheit. This discovery tells us that room temperature superconductivity is not ruled out by fundamental constants, stated Chris Pickard, a co-author of the study. It gives hope to scientists. The dream is still alive. Understanding how these fundamental constants influence superconductivity is paramount. They dictate the stability of atoms and the vibrational frequencies that form Cooper pairs of electrons, which are essential for superconductivity. The researchers contend that if the upper limits of Tc are indeed as high as they propose, then the prospects for discovering practical room temperature superconductors are not just theoretical, they are attainable. Kostya Trichenko, the lead author of the study, emphasized the practical implications of such a breakthrough. The wire would superconduct instead of heating up. He explained, "This fundamental shift could transform everyday tasks. Imagine boiling water for tea becoming a challenge of engineering rather than a simple chore." The implications extend far beyond the scientific community. Achieving room temperature superconductivity could lead to significant advancements in energy transmission, medical imaging, and quantum computing. It could pave the way for efficient power grids, cheaper magnetic levitation trains, and accessible quantum computers, transforming industries and everyday life. Moreover, the study has been corroborated by independent research, bolstering its credibility and inviting a deeper inquiry into the implications of fundamental constants on matter. The findings highlight the intricate balance that governs the universe and how it affects technological advancements, urging scientists to push the boundaries of current knowledge. As scientists continue to delve into the complexities of superconductivity, the promise of a room temperature superconductor feels closer than ever. The journey toward this holy grail of materials science not only reflects humanity's relentless pursuit of knowledge but also signifies a potential paradigm shift in how we understand and utilize electricity. With ongoing research and innovation, the dream of practical room temperature superconductors could soon transition from fantasy to reality, reshaping the landscape of technology for generations to come.